All right. Here we'll be looking at question 4, which reads, a spring is supported so that it hangs vertically, as shown in figure 4.1. Let's see. I wonder whether, oh, they've labeled it, thankfully. So now we know this is the spring, and this here is the mass M. Different masses are attached to the lower end of the spring. The extension X of the spring is measured for each mass M. The variation with X, the extension of M, the mass, is shown in figure 4.2. The mass on a spring, and it looks like it doesn't really start to extend very much until you've got to like here. And then it uniformly increases. And so if you recall Hooke's law, then we say when the force applied to an object is proportional to its extension, or when the extension or compression of an object is proportional to the force applied, we say that it obeys Hooke's law. It looks like this thing obeys Hooke's law once you get to a force of whatever, the force due to gravity of a 50-gram mass is on the planet that they've done this experiment, or the gravity field they're in. We could probably assume Earth, right? Let's assume Earth for this. And so, yeah, to make it a bit more clear, sort of what we're talking about, let's actually calculate that. So if we had a 50-gram mass, 50 grams, well, that's 0.05 kilograms, right? We divide by 1,000 and we have 0.05 kilograms. On Earth, we know things experience 9.81 newtons for every kilogram of mass they sort of possess. That's their gravitational field strength. So just like we saw an electric field strength is the force per charge, in a gravity field, it's the force per unit mass. So something that's 0.05 kilograms times 9.81 newtons per kilogram means that there is a force here of this mass, 50 grams. We could sort of make a corresponding force extension plot. Say once you get to 0.4905 newtons, then it obeys Hooke's law. But it doesn't obey Hooke's law from 0 newtons up to that many newtons, right? It's like this is a curved line indicating it's not obeying Hooke's law down here. It obeys Hooke's law from here to here. So we could kind of say, because the extension is not, I feel like always, because it is for most of it, right? Like from here to here, that looks pretty good. That's a Hooke's law, sort of obeying Hooke's law. Because the extension is not always proportional to force, the spring does not obey Hooke's law. I imagine some students might say the spring only obeys Hooke's law once a 50-gram mass has been applied, and so then the extension is proportional to the force applied. Sort of like up to sort of whatever 160 millimeters. That might get the mark too. If you just sort of say it obeys Hooke's law, but only here. But you say, well, if you look at the entire sort of data set, it doesn't obey Hooke's. Like this curved part of the graph sort of disqualifies it from obeying Hooke's law. But it does obey it over this part. That's the way physics goes. Now you want to state the form of energy stored in the spring due to the addition of the masses. And so we would call that form of energy, it's a form of energy that's due to the change in the shape of an object, right? So it's getting longer and longer, it's extending. And so that's a potential energy because it's not energy of motion. And we would call that elastic potential energy. Describe how to determine whether the extension of the spring is elastic. So in elastic deformation, is one that when you remove the force that's causing the extension or compression, does the object go back to its original shape? And so you kind of want to put that into your own words by saying, in order to determine whether the extension of the spring is elastic, remove the masses and see if the spring returns to its original shape. Okay, if it does, then it was an elastic deformation. Okay, the extension was elastic. If it does not return to its original shape, we call it a plastic deformation. That is a permanent change to the spring. So that's how you can determine it. Remove the load and see if it goes back to its original shape. If it does, it was elastic or deformation. We want to calculate the work done on the spring as it is extended from 40 millimeters to 160. So the work done as it is extended from 40 to 160. Okay, what is the work done? So it's going to be the area of this, which you could say is a rectangle plus a triangle, right? We could calculate the area of this rectangle, the area of this triangle, and then that would give us the total elastic potential energy. That total shape is a trapezoid. Calculate the work done on the spring. So the work done is equal to the elastic potential energy that it possesses, right? Work and energy is sort of the same thing. So the work done is the force times the displacement. We see the displacement, but we have to sort of, again, translate that into force. And so, yeah, we are going to have to do that. Remember, we're looking at mass against extension. So the area underneath this curve won't give us the elastic potential energy of the work done. We'd have to transfer these values of mass into forces, right? Because it's force times displacement. So it's the area under sort of the corresponding curve. If we had, again, newtons of force times meters of extension, a newton meter is a joule, right? And you look at sort of the units here, they want it in joules. So that's what's tricky about this, is you have to sort of look at the data that's given and do some calculations to sort of translate it all over here. So if this is 50, then this I think would be 75 right in between. This is going up by 55, 60, 65, 70, 75, 80, 85, 99. So it's gone by 5s, 55, 60, 65. So this is 70 grams all the way up to 145 grams. So then, just like I did before, so let's make it a bit more familiar. Let's calculate the forces corresponding to these, keeping in mind that we'll assume it's on Earth. And so the weight is the force due to gravity. It's equal to mass times G, right? That'd be the weight. The weight is the force. So we'll take our 0.07 kilograms times 9.81. We'll take our 0.145 kilograms times 9.81 and calculate that first. So if I've got 0.145 kilograms times 9.81 newtons per kilogram, I've got 1.42 newtons there. So 1.42 newton force. 0.07 kilograms times 9.81 was 0.68 0.6867. All right, so I have those forces. If I think about the height of this rectangle, the length times the width, then the length here is going to be this, sort of 0.6817 newtons. Now, from 160 minus 40, that's 120 millimeters. A newton meter is a joule. So see, I've sort of forced my calculation into convenient units that are going to give me my final answer joules. So I got 0.6867 or 0.687 times 120 times 10 to the negative 3. So the area of this rectangle, once I've, converted it into force here, these masses into forces on Earth, then the elastic potential energy just sort of from, this part would just be 0.082 joules. Now I've got this 1/2 base times height triangle to contend with. So I'm going to do 1/2. Let's just make this the base because I already know it's 120 by 10 to the negative 3. I'll write this over here. So I have 1/2 the base times the height now. And so this again goes from 1.42 newtons right here down to 0.6867 newtons, 0.687 newtons there. So I need sort of, what is sort of the height right here? So it's going to be 1.42 minus 0.6867 or 0.733. So if I take that times 120 by 10 to the negative 3, and then times 1/2, I get the area of this part, oh, 0.0439. 0.0439 plus 0.082 equals 0.126. So I get 0.126 joules. Let's see how well we did. Going to the mark scheme. Get nervous here. Moment of truth. Question 2, question 3, on to 4. And what do we got? The straight line does not go through the origin. The force is not proportional to the extension, so it does not obey Hooke's law. Okay, good. The elastic potential energy, good. Remove the force. Masses in the spring returns to the original length if elastic. We said that, good. The work done is represented by /linked to the area under the line, look, times G, we did that, 0.127. Is that what we just got? 126. Curses. Well, you might say, well, maybe that's close enough. They give it to us here. Maybe they say, nope, it's all wrong. You lose that final mark there because you should have rounded it to 2 significant digits. And if we would have done that, if we would have said, oh, 0.126, let's round it to 0.13, then this little, rounding error here, did I not use 9.81? Yeah, so somewhere along the way, I was maybe a little bit more precise. So I rounded it down. But you get the idea, right? Pretty good, not too bad.